Motion is a change in position of an object with respect to its surroundings within a given interval of time. Specifically, when involving an object with a mass, it can be described with terms such as displacement, a change in an object's position, speed, the rotation, the ratio of distance to time in which a distance was covered, velocity to the object's displacement divided by interval of time, and acceleration to the rate of which an object's velocity changes. Some different types of motion include rotational, when an object moves along a circular path about a fixed axis; periodic, a type of motion that repeats itself after certain intervals of time; and projectile motion, when an object is thrown or projected into the air, is only experiences the force of gravity.
In the provided helicopter problem, it is given that we launch at time little t, which is equal to negative capital T, a variable that represents an unknown but constant time. It is also given that it flies for time t and travels for a horizontal distance t. The other variables that are involved are alpha and beta, which are known constants, and we're also going to assume for this problem that they are greater than or equal to 0. As we have learned in calculus, we know that with the position function, we can derive it to get the velocity function and take the second derivative of the position function to get the acceleration function. Likewise, this means that if we perform the integral of an acceleration function, we can get the velocity function, and if we perform the integral of that said velocity function, we can then get the position function. Since we were given the acceleration function with this helicopter, we were able to integrate that to get the velocity function and further integrate that to give the position function, and we were able to have the x and y components for all three of those equations.
With the given information from the prompt, we are able to infer that the helicopter's acceleration is a positive x direction, and with t equals 0, the acceleration will be given the sign and increase in a negative infinite direction. When t equals negative big T, the y component of the acceleration will be the positive y direction, which will move in the helicopter upward.
For the velocity in the y direction, we are able to take the roots, the values of little t where velocity will be equal to 0, and we are able to get that little t is equal to plus or minus big T and 0. From the acceleration graphs, we're able to see that on the interval from negative t to 0, and then from 0 to t, the velocity is positive. However, once little t is greater than or equal to big T, the velocity of the helicopter is then in the negative direction. Essentially, the helicopter goes up, stops, goes up again, stops again, and then begins its decline. Here we have two position versus time graphs representing the x and y components of the position function that we obtained through integration of the velocity function. We are able to both infer from prior graphs, functions, and statements, and see on these graphs that the helicopter reaches the ground after a change in direction where it goes in the negative x direction.
Sense making symbolically. Linear relationship, also called direct or positive, this is when one variable changes and the other variable also changes proportionally. This produces a straight line when graphing. Then there's an inverse relationship. An inverse relationship occurs when two variables change in opposite directions. For example, when x increases, y will decrease, and when y increases, x will decrease. Exponential relationships, a relationship that occurs when a constant change in an independent variable changes the same proportional change in terms of a percentage increase or decrease in an independent variable. Solving for the symbolic unknown. Off to the left, we have the acceleration of time equation. Then we have a velocity equation. And we know that the initial time is negative t and the final time is positive t. When t is an unknown but constant time, by solving for the x component of the position function with respect to the final time t, we were able to solve for the change in the distance and the change in direction. By delta x equals d equals 2 beta over big T squared divided by 3. By solving the y component of the position function with respect to time, final time, t, we are able to solve for the change in the direction in the y direction. Having solved for the change in x position and change in the y position, we are able to first solve for t squared and substitute into the equation above. Once we have figured out our t squared, we're going to solve to our delta y, and then we can solve for t.
With the knowledge of the different relationships of variables and our equations for the change in the x direction, change in the y direction, and for the unknown constant t, we are able to determine how one variable affects the other. Since we know that alpha and beta are known constants and big T is an unknown constant, we can see how t and d, also known as the change in distance in the x direction, affect one another. In the equation for delta y, we are able to see that d is a multiplicand of the fraction alpha divided by 35 beta. Since alpha and beta are those known constants and knowing variable relationships, we can see that the horizontal distance away that the helicopter lands, d, and the change in distance in the y direction have a linear relationship. As one increases, the other does as well, proportional to the change. In the equation that determines the change in distance in the x direction, also referred to as a horizontal distance away that the helicopter lands, d, we are able to see that it has a linear relationship with t, the unknown constant. As t increases, since it is the numerator of the fraction and it is being squared, and the denominator will stay the same, the fraction as a whole will increase, as long as t is greater than 1. That fraction acts as a multiplicand with the two betas, so the relationship will be linear.
Next, we're going to move on to the reflection. First, I'm going to start off with the similarities. This problem also connects with the learning introductory physics with activities, the section 2.9 motion graphs, because it discusses position versus time and velocity versus time graphs, a key part of the inclusion of relevant graphs and diagrams aspect of this problem. This problem connects to the learning introductory physics with activities, section 2.13, using integrals in physics, because it discusses using integrals to obtain other functions. One of the core parts of this helicopter problem is we use integrals to obtain our velocity and position functions. Continuing on with our reflection, we have our specific similarities. We have activity 1, where we're throwing at a cliff, really, on the screen, and it's talking about a ball being thrown off a cliff, yada yada yada. And we see a lot of similarities with activity 1, as we saw in our written homework from week 3. Here we had one of our first problems, including two-dimensional kinematics, motion involving both horizontal and vertical components. Another problem sharing similarities to the helicopter is the in-class problem we discussed regarding marbles being pushed off the table, where we're also able to work with the vertical and horizontal components of motion and get a grasp on the impact that different angles had on the distance that an object travels. Then finalizing off our reflection is our differences, because other than the problems listed associated with their similarities, the majority of the work we have done consists of many differences. This problem does not involve performing dot products, unit vectors, or the majority of the chapter 3 forces. Like, for example, activity 2, the gymnast, seen for the week 5 written homework, in addition to being discussed in class, does not share much of having anything in common, as it discusses forces, specifically tension, involved with mass, but not the vertical and horizontal components of motion in relation to time.